We're continuing the workshop by installing some of the available bindings for Red System. Red System is mostly the core language by now, and it has a small runtime that includes some print functions, but it doesn't have many standard ways to reach the outside world yet. Those are in the bindings with external libraries. And this is shown here is the contributions page from the Red website, where most of the currently available bindings are listed. And most operating platforms out there are based on the C library, and based on the C language, and by being based on the C language, almost all applications are based on the standard C library. For all the bindings that are listed here, you need the C library as a base. And the other bindings include the C binding automatically, but it needs to be installed. So we'll start with the top one, the C library. And the C library is actually complete at the level of the NCC definition from somewhere around 1980. There's a famous book, NCC second edition, that all C programmers have, and in the back it lists the extent of the standard library, and I bound all those functions. Newer C libraries have more functions, but if you start binding those, you have to be very careful on which platforms they are and are not available. So the current extent is the NCC second edition book definition. And the bindings that I wrote are kept in not in Git repositories and not on GitHub, but they're kept in Fossil repositories. Fossil is a very nice alternative distributed versioning control system that is much smaller than Git and more portable to Windows. And you see here the standard page of a Fossil repository, where you see a graphical timeline of what happened. And the C library is actually interesting because I made a branch in there that you see in the graphical timeline. So far all the bindings have been straight development lines, and since a few months I try to keep them compatible with the release state of Red System, and the current release is 0.24 with the first floating point support. But after that I wrote a few floating point test programs, and we found a number of bugs. So the Red System 0.24 release has floating point, but with a number of bugs still in it that are fixed in the development version in Git. And because I now try to keep the bindings compatible with Red release packages, I made a branch in Fossil for the work for the Red version with the floating point fixes. So if you install the Red System 0.24 release, you can simply keep using the trunk version of the Fossil binding repositories, which is the same as the master branch in Git. Fossil calls that trunk. And you see trunk stopping halfway down the screen, and there I made a branch which I call the developing, and that is synced with the master branch in the Git repository of Red System. And we installed the daily master branch of of red system, so we now need the developing branch of the C library binding if we want to get the floating point fully working. So you need to have the top one. Let's see where I don't even remember where the downloads are in my own fossil repository.
You just click on
Maybe,
the commit link and you get the download link after
yeah.
that.
If you the top link, the top check-in, yeah, that's the top of the developing branch. Oh yeah, tarball, or you can choose the zip. And now we're really doing the same thing we did in GitHub, simply downloading the really current state of the repository. And then you unpack that.
Unpack it where?
And as with all the other red system stuff, we need that in the red system folder, right? Yes. The same place where you put the REBOL executable. Oh, now it gets an awkward name. It needs to have the same name as the repository name. So it needs to be called red-C library or something like that. Exactly the same spelling as you see in Fossil. And it's probably not capital sensitive in here from the URL. On Linux it would have to be with a capital R. That's probably not necessary on Windows, but to be safe you should best copy the name from the Fossil URL, right, like this. Now if you look into that folder, all the bindings have a top level because the bindings are very small, and the C library binding is actually the only one where the binding is in two files, plus the separate copyright file. I put everything under a BSD license, pretty much like Red System itself. So you can do almost everything with it as long as you keep the copyright notice included. The C library as defined on most Unix systems is actually divided into two binary library files, the C library itself and the math library where most of the floating point functions are. And since Red System has a direct correspondence from bindings that you write with the import statements that we saw earlier, and the binary files where the libraries reside in, the binding is here also split in two files. So the C library file binds the C library binary, and the math binding file binds the math library. And in Windows those are the same library file, but on regular Unix systems those are two separate library files, and that's the reason why they're divided in two files. So if you only need the C library functions, the very basic functions with communicating with the operating system, you only import or include, just like in C, the C library file. And if you also want to do extensive floating point mathematics computations, you include the math library. And it's actually a little easier than in C, because in C, if you want to do math, you would have to include both the C library header file and the math header file. but in Red System you can nest them, and it will detect that a file is already included. So I set up the binding so that here, for example, the math library basically, well, not necessarily I think, but basically if you use the math library, it's pretty certain that you will also use other C library functions. So it's not a hard dependency, but the math file includes the main C library file. So if you know that you want to use the math functions, you only have to include the math library file, and that will include the C library file. So to cut down on the header files in C, if you program in C or in C++, you have really many header files, and that's not very user friendly, not very programmer friendly, and especially not very REBOL-like. So I try to cut down on it by having libraries include each other if you know that you're going to need them anyway. So that's the basic layout of a binding repository. The other bindings follow the same principles, and there's an example folder with a few programming examples, and at the moment that's the only documentation that's available for most of the bindings. Only a few example programs that I also use to develop and test the bindings itself, so I need those examples anyway. And for the C library, there are actually only 2 examples that use Floatingpoint, so they're also quite new since the Floatingpoint support in Red System, and they're 2 very well-known program examples for computing a Mandelbrot fractal and rendering it only in ASCII in the terminal at the moment, and a function for computing Fibonacci numbers. And that's actually not an optimal way to compute Fibonacci numbers, but a recursive way to let you test some stuff. Wait a minute, the Fibonacci is integer, right? Yeah, I'm forgetting. The Fibonacci is actually not using floating point. So where we have an integer and function calling example here in Fibonacci, and the floating point example in Mandelbrot. And what I did recently is, because they're actually benchmarks, they're not very comprehensive, they're very specific tests, but it is interesting to compare them to other languages. So what's in here is not just the Red System example, but I wrote examples for 8 languages, including Red System. Some of them are combined. The .r file is a REBOL program that works unchanged in both REBOL 2 and REBOL 3. So these are 7 files, but they actually compare 8 languages. And if you open the Red System file, you can see how it's programmed in Red System. It includes the C library file, and there's no search functionality yet, so there's no search path for the includes. So you have to give the path yourself, and to make it usable. Oh, well, actually, I'm even wondering if it's right now. I think it searches 1 too deep. It goes 2 directories down. I'm not even sure why it's like that. Can you open the Mandelbrot to see how it's in there? Oh, I'm not even sure this works the way it's put here. Well, we'll see. Anyway, this is the floating point example. If you scroll down, you can see what's in there. They're fairly small test programs, And actually the only reason, the only good reason to put it in the repository of the C library binding is that the Mandelbrot computation itself uses straight floating point. That's in the core of the Red System compiler. But the only, you can see it doesn't include the math library. It only includes the C library file. Because the only C library stuff that's used here are the timing functions, really. If you look at the bottom of the file, it takes the time when before the computation starts, and then when the computation has ended, it takes the time again and computes the difference. And the subtract time function you see there, and the now time functions are functions from the standard C library, and I've tried to give them names that match REBOL function names. And the names of the C functions are very arcane and envisioned in the early 1970s, when it was thought probably that that computers were always going to be limited to specialists in wide lab codes. But now that many more people are programming, it makes sense to do it the way REBOL tries to do it, by using more normal English names. So I've renamed the C functions. You're calling the C functions straight away usually, but by other function names that are much more REBOL-like and much more English-like as REBOL is meant. And Red takes those same principles, so I try to adhere to them too. There's also, you see, a toFloat function. That's also, and the form integer function, and those are also functions straight from the standard C library. And clocks per second is a standard value that is different for different platforms, but it's just an integer constant. And in C you would, it's a convention to write integer constants in uppercase, but I don't really care for that convention, because this is Red is supposed to be as much like REBOL as possible, and it has a very dynamic nature, so it shouldn't really make a difference whether a name holds a constant or a dynamic value or a dynamic function or whatever. So I write constants in lowercase as well, following the REBOL conventions. So for C programmers it will take some getting used to, and but for REBOL programmers it looks very familiar, and for REBOL programmers it will take some getting used to that in Red System you're actually working on the C level, and like is done here, you can call C functions directly without any intermediate level. The Red System compiler compiles just the way a C compiler compiles. So you call the C library functions that are programmed in C, you call them straight away from Red System. Now, having seen this code, let's try to compile it. So we recall the compilation line, and now instead of the tests folder we have to go to the Red C library folder. Right. And then the examples folder. And then let's try the Fibonacci. Oh, that's why. Oh yeah, I forgot. I moved I started with the Mandelbrots and then I added the Fibonacci, so I moved them to 2 separate folders. And that's why we include the headers from 2 levels up. So this should work. Right. So we have a Fibonacci program now. So let's try to run it. And to have in the program is a generic Fibonacci function, but you have to call it with a parameter. And if you program it recursively, as is done here, just as a test, the time it takes increases basically exponentially. We had an argument about that in the REBOL 4 ALPMI world. What's the order of computation? And the 2 experts disagreed, and then I think the verdict was that it was more or less an exponential order. But in any case, if you compute Fibonacci numbers recursively, it takes a lot more time for higher numbers. So to get a good range for testing, I chose the number 35. And as you see, the Fibonacci number of 35 is 9 million something. And it takes under a second. So to have a meaningful test result, you should either run it on a much slower machine, as I did, or you have to compute a higher Fibonacci number. But actually, I develop on Linux, and then I test on Syllable, and there you have the time command. And I don't call Fibonacci directly, but I call it through the time command. And the time command will tell you in sub-seconds how much user space processing the process took. And it will tell you how much system processing went on within the kernel of the operating system. And that's with probably with micro or even a nanosecond resolution. And what you get here is just the output of the C-time functions that you saw in the program. And on most systems they only compute in seconds. So the times that you get reported here are fairly meaningless. But if you run this on a Unix system through the time command, you get a meaningful sub-seconds time. And what we can do now is increase the number. So if you go back to the source code and you change the 35, which is defined on top, to 40, for example, and that seems a small increase, but the processing time actually increases a lot. So this should give you a computation of several seconds that is measurable by the standard C library time functions that we used. Yeah, recompile it, and then relaunch it. See, this will take a while. Oh, it's still under a second, so try 45. See, processing time increases explosively. So now we should get a meaningful... oh, the report is still 0. So there's probably something still wrong with the time measurement. We found that the clocks per second is the constant value that we divide by to get the seconds. According to Unix standards, it should be a million ticks per second. but we found out that it's supposed to be 1,000 for Windows, and I changed that 2 weeks ago or something, but apparently it's still not right. So
you should check it. Check the value in the C library source code.
In the developing version that we downloaded from Fossil, it should be 1,000, but we can check.
Just check it to be sure.
The C library file. Two levels up. The C library file. It's a fairly big one, about 2,000 lines, I think.
Search for clock.
A few pages down. It uses the C convention, start with defines for constants, and then struct definitions, and then the functions. So I changed the clocks per second to 1,000 for Windows. So it should be correct, but apparently it's still not correct. So when I'm back home, I'll have to look into that. I'm not testing on Windows, so actually probably Ninat will have to look into it. or Freddy. That would be nice.
The motherboard code should work.
Yeah, but if the time report is incorrect here, then it will also be incorrect for Mandelbrot. But we are using the newest version here, where I switched the value for Windows. So it should have been correct, but I couldn't test it because no Windows. So that still needs to be fixed. Okay, let's compile the Mandelbrot. And you see that Freddy already needs to switch between about 3 windows here. We just had an off-film discussion about IDEs that Ninat has planned. And what I'm currently doing is I've put this workflow in Genie, a nice small generic IDE, and then you can have a few function keys for compiling for your compilation setup, and you can compile from Genie, where you edit several files. But also when you do that in Genie, you notice that that it's really that there is stuff that oh, that's weird. We do get a process report here. Oh, you already knew that. Oh, then there's something weird with my Fibonacci code apparently. So I'll probably have to look into it. It's probably a difference between Fibonacci and Mandelbrot. Although I copied the code, I must have done something wrong. Okay, so here we see that the Mandelbrot was rendered in slightly under a second, but that includes the time for rendering it to the prompt, and that skews the processing time. So if you really want to have a meaningful comparison with the other programming languages, I did the same thing here. There are comparisons of 8 programming languages, REBOL-like languages, and Ruby. And if you want to do a clean comparison, you either have to switch off the output to the terminal, or you have to increase the number of iterations that the Mandelbrot fractal computation does to make the computing time longer, so that the rendering doesn't skew the results anymore. But I did the comparisons, and we discussed them last week. And in general, it turns out that at the moment Red System is for generic programming, for integer computations and function calls that every program does. It's basically as fast as if you compile the equivalent C program with the GNU C compiler. but don't use optimization. So the unoptimized output of GCC is basically as fast as the Red System compiler output, and that's a very good result because the Red System compiler is also currently unoptimized. So if Nenad has achieved that by now, then when he makes an optimized compiler there in the future, there's a very good hope of really approaching the result of optimizing with the GNU-C compiler. And actually I was surprised by the difference of optimizing. I thought it would be maybe 30% or something. But actually optimized GCC programs are pretty consistently twice as fast as optimized programs. So there's still a big gap there. So at the moment Red System is half the speed of fully optimized C, but it's the equivalent speed of non-optimized C, and that's very good because modern compilers are very slow because they do all this global optimization, and Red is supposed to become a YIT compiler, and then you need really fast compilation. So it's really meant to be a non-optimizing compiler at first, because compilation speed is also very important for the YIT compiler. And so the current result, that it's almost equivalent to unoptimized C, is a really excellent outlook for the coming YIT compiler. There's one thing, we haven't done really clean comparisons of this floating point Mandelbrot computation yet. So in the preliminary results, it seems that there's still if you do a lot of floating point computations in the Red System, it seems to be half the speed of unoptimized C if you use a lot of floating point. But we're not really sure that. Next week I'll try to make clean comparisons, because Nenad thinks it should be faster. But as long as you don't use floating points, you can currently expect the same speed as unoptimized C.
We didn't install any libraries.
No, that's a good point. As I'm pointing out along the way, Windows is weird in a lot of ways. And one of the things is, although I said that basically all operating systems except a few weird ones are built upon the C language, and that means that that user programs should build upon the C standard library. Windows doesn't. Windows programs are built on the Windows kernel part that faces user space, and that is different from the standard C library. So in the Hello World example, we already saw that it binds an extra function to color the output in the terminal, and it binds that to the Windows kernel library, which is the interface from user space to the Windows kernel. But usually such functionality on all other systems is in the C library. And we're testing the C library binding now. And on Windows you actually have to install a separate C library to get that functionality that is standard on almost all other systems. But of course that was defined by Unix in the early 1970s, 40 years ago. And everybody uses it except Windows. So on a cleanly installed Windows system, you won't have the C library. But because the C library is so important for all other code, all other programs, on many things that you install on Windows, you get the C library included. and according to Microsoft it is a part of the Visual C++ runtime. So if someone makes a program with Visual C++ and they distribute it, in most cases the Visual C++ runtime will be included, and that will include a C library according to the C standard that we bind here. So there is a possibility that if you want to run this program that you need to install the C library in the form of the Visual C++ runtime, but this is of course a developer's machine, so it's almost impossible that the C library is not on there somewhere. So indeed this worked right away. But we'll see that in the next bindings. Any other questions? Okay, so these are the two examples that are included in the C library, and all the other bindings build upon the C library. So now that we have that installed, we can take the next one. So go to the red contributions page, and then take the next binding that interests you. GTK is a cross-platform toolkit for creating graphical user interfaces. So that's what most programmers will need to do their work, to create input forms in graphical windows, stuff like that. And you see that unlike the C library binding, there's only one timeline here. There are no branches yet. So you can simply take the top check-in and again download the tarball or the zip. The zip will usually be easier on Windows. And the tarball will usually be easier on all other systems. And like the C binding, just install it in the red system folder next to all the other stuff. And then again rename it to the same name as in the fossil URL, because that's what the include paths in the programs use. Right. Be advised that I'm thinking about dropping the red prefix. I haven't decided yet. It would be slightly simpler, I think. So if I do that, I'll probably do it next week, and then you'll have to rename your folders. If you were to check out new versions of the bindings. So stuff like that is still shifting as we develop red and the bindings. So you'll have to make some changes now and then when we change our mind or make bug fixes, like in the Floatingpoint developing branch or stuff like that. So we try to keep things as stable as possible, but it's really heavy development, so some things will change now and then. Yes, again, an examples folder. And actually there are several examples in here. Everybody always wants to see the hello world example, and we already saw one for red system in the console, in the DOS prompt, here on Windows in this case. And I wrote several versions of hello world for a graphical program, and to to show you why they not decided to implement a new language. As far as I'm concerned, it's very nice to look at these GUI examples, because the GUI is one of the the strongest point of REBOL, and we're trying to approach the same ideals in red. And actually that is planned for red, but actually you can get very far in the low-level red system already. So to really get an idea of why we're creating a new language, it's very nice to look at these hello world examples. And the simplest one is that one, yes. And we've already talked about the red system header with the standardized metadata. So almost all of this program is the metadata, so you only have to, that doesn't matter, you only have to, that's just documentation. The only thing you should look at for this example is the bottom two lines, which are the real program. And in REBOL this would only be one line, just the bottom line, and in REBOL it looks fairly much like this. And the only thing that's really extra in red system is the top include line, because as we saw, like in C programs, you need to include header files. In this case they're not really header files, but they're the file with the binding. And in C you would need to include the C library, which you base yourself on, and then you'd have to include the GTK library. And the GTK library would actually consist of many parts. And for example, you would need to include the header file for the glib binding that GTK is based on. And we made that unnecessary in red system. So you only need to include the GTK file, and then that will include the glib binding and the C library binding that it's based on. So it's only one include, and then you have all the GTK functionality plus the C library, because you know that that is also included. And then it's only one line to create a window with a small graphical user interface. And well, depending on how familiar you are with graphics programming, this may or may not be impressive. And to show you what the difference is with other programming languages, I wrote the same example, which has exactly the same functionality, not as hello world, but as goodbye cruel world. And I wrote that in red system as well, but I wrote it the way it would be written in other programming languages. So if you use GTK in other programming languages, you have to write it this way, very much this way, although this is still red system. But this is the code you have to write, for example, in C, which GTK itself is written in, or in programming languages like C, where you need to program all the GTK functions to get this result. And I hope you can see the difference with the way it is written in red system, the way we want it to be written, as you just saw, in just one line. Now there's also the matter of, this is a very simple example, and you could complain that it's not a real-world program. And you could say, for example, that most hello world examples also have a title that they set in the window title bar. So I have also a version that extends it with title. And then you see that it becomes slightly larger. And because there's an extra construct in there, we now have to use a block between square brackets, as is the REBOL convention. Actually, if you look at the header file with the metadata, you see that curly brackets are used there, and double quotes. And those are two ways to delimit string values. And string values on one line are usually delimited with double quotes in REBOL and in red. And multi-line strings must be delimited by curly brackets. But what you'll see most in REBOL and in red system are square brackets, because that's what you use to structure code. So here we see the first example where you need a REBOL-like block to add the extra construct of the title bar, of the window title bar value. And as you see, if you compare it with the initial example, you only need to add a string value, and it will automatically be interpreted as the window title bar value. And because we now have two constructs, namely a title string and a label construct, you now have to put it inside this square brackets block structure. So when you start making it more elaborate, of course the program grows, but it still stays quite small. But you could still object that this is not a very extensive Hello World example, so there's a still more extensive one, the dressed up Hello GTK world. And here you can see how stuff is developed if you start extending your GUI. And on top is actually an extra thing where I'm interested in the GTK version that you're using. If you're using this on Linux or on FreeBSD, then it's almost guaranteed that the GTK library is included in your operating system, and in many cases it's actually used as the standard GUI library of Linux and FreeBSD. For example, in the GNOME desktop and many other desktop systems. So we're interested in which GTK version we find in the platform. So the first two lines find out what your GTK version is and print that value to the console for diagnostics. And then we have the graphical GUI specification again. And what I implemented is a declarative dialect, quite like the REBOL dialect for GUIs. And you can see that besides the label and the window title, you can just start adding other extra constructs declaratively. So we still have the block with the GTK view definition. And we still have the Hello World title bar string. And we have extra constructs now, starting with two numbers, 170 and 90. And those are interpreted as the initial size of the window. So the window that opens here will have a default size of 170 by 90. And then the GTK position center is an integer constant, and you will notice that that is the third integer in this specification. So the dialect needs to make some effort to detect that this is different from the window size. So there's a limit to how you can build dialects in red system, and those limits will be lifted in red. red dialects will be much more flexible, but I have stretched it so that you can have 3 integer values here in a red system dialect. And if it sees the third integer, it assumes that the first 2 integers are the window size. So the third integer must be the position specification. And then we can use the GTK position center value to center the window on the screen. And you can add that, or you can leave it out if you want, or you can put it in a different place. But the dialect is primitive in the sense that you can't put it in front of the 2 integer values for the window size, because then it will get confused between the window size and the specification for the position. So you have to be a bit careful how you use this dialect. So it's not as user-friendly as REBOL dialects, and that's why we're still eager to have red, because this is an exploration of how far you can get with a red system, very low level and very efficient dialects, but it will be much more user-friendly in red, the high level language. Now, looking further in the specification, we see an extra icon construct. And the icon is actually a function call. And it takes 1 parameter, a string with the name of the file that it needs to get its icon from. And in real REBOL code, a file data type would not be a string data type, but it would be prefixed with a %sign, as we already used in the terminal when passing a red program to REBOL. But file types are currently not defined in red system, so I'm using a string type to pass to the icon function, and it will take that as being the file name where it needs to load the icon from. And I implemented a fairly flexible error detection in there. If the icon function doesn't find the file, it will only issue a warning, and it will then return a null pointer in C terms, and that's a very low level detail that's dangerous in C code, and thus also in red system code. But the GTK view dialect detects this null pointer value, and if the icon function returns that, it will know that the icon function somehow was unable to load the icon, probably because the file was missing. And then you will get a warning from the icon function, and then a subsequent warning from the GTK view layout function that the icon was missing, or that some element was missing. And if it does return an icon, then the GTK view function will simply add it to the window that it is constructing. Now, and then following that is the most extensive construct, where we start nesting block structures. We have a VBox function, which is a red system function that takes a block like the GTK view function takes a block. So a VBox specification can be much more elaborate. And indeed we see 2 constructs in there. A string data type that is taken to be a label value. So in the first view examples we saw that we used a label function, and the label function was interpreted by the GTK view function to add it to the window. But I implemented a shortcut in the VBox function, where if it encounters a string data type, the VBox function will interpret it as a label, and will interpret a label and will create a label automatically, a label object, and it will add that to the box object. But you could also write it explicitly. So if you write a label in front of the string, you will get the very same result. So it's a shortcut to leave out the label specification. And that way I'm trying to make the dialect as short as possible. Next we get an HBox specification for a horizontal box. The VBox is for a vertical box, and that way you can structure and nest your layouts. And in this case, within the horizontal box you get a button object, and the button can also take a fairly extensive specification, so it needs to be in a block structure again. And we already saw that the GTK view function can take integer values, and it takes that as the size of the window. And the button function does something similar, and it takes integer values as the size that the button should get. So we define a button with size 50 by 25 here. And then the button object can also interpret a simple string value, and it takes that as the label that the button needs to have. And I don't even remember it, but I think that here also you're free to write label quit instead of just the quit string, and I think you will get the very same result. And then last we get a new construct. The word GTK quit that is prefixed by a colon is the red system way to write the address of a callback function. And a callback function is defined as a function that conforms to the calling conventions of the operating system. So you can use it from operating code, and you can pass it to external libraries, and the libraries will be able to call this function because it has a known calling convention. And the GTK quit function comes from the GTK library, and the GTK quit function is the standard function that you call to quit a graphical GTK program. And what we want to do here, we've added a button that says quit, and if you press that button, if you click it with the mouse or press enter on your keyboard, we simply want to quit the window, we want to quit the program. And in order to do that we need to call the standard GTK quit function, and the button object can take that as just the address of the function, the way red system passes it. And if the button detects this